Today we are going to discuss our next sensor, that is force and torque sensor, that is used to measure the reaction forces developed at the interfaces between mechanical assemblies. Used to measure the reaction forces between interfaces between mechanical assemblies. That the principal approach for doing this are the joint and wrist sensors. Joint and wrist sensors are the principal approaches for doing this type of sensing. A joint sensor measures the component of force and torque acting on a robot joint. We have shoulder joints for a robot arm. We have shoulder joints, base joints, then elbow joints, wrist joints, etc. Okay, so this joint sensor measures the component of force or torque that should be exerted on that particular joint. Okay, for a joint driven by DC motor, the sensing is done simply by measuring the armature current. So by measuring the armature current, we know the exerted force or related proportional. So that is proportional force that is applied to the armature can be measured by measuring the armature current. Okay. Then wrist sensor, that is that should be connected at the end effector points, that mounted between the tip of the robot arm and the end effector. Mounted at the tip of the robot arm and the end effector. Okay, they consist of strain gauges that can measure the deflection of mechanical structure due to external forces. Actually, we know that what I mean by a strain gauge. In strain gauges, if we apply a force or a stress, the part or material manufactured by the strain gauge varies resistivity, having some elasticity to that particular material. So it changes its length, or that way changes its resistivity. Okay, so that type of strain gauges are used to measure force or torque at wrist point. So today we are going to discuss another force sensor, that is wrist sensor. Okay, so you can see the diagram of a wrist sensor here. It is very small, sensitive and light in weight. Actually, it has a 10 centimeter diameter and a 3 centimeter thickness. It is constructed using aluminium. Usually have strain gauges. Strain gauges changes its resistivity when we apply a force on it. In wrist sensor, a strain gauge mounted on 4 deflection bars. You can see it in the diagram. We have 4 deflection bars. Okay, 1 gauge on each side of the deflection bar. So total of 4 deflection bars. The strain gauges on the opposite opponents of the deflection bar wired differentially to a potentiometer. So thereby we can measure the resistivity change. Okay. Then since there are 8 pairs of strain gauges are oriented normal to the x, y, z axis, the force and moment determined by properly adding and subtracting the outputs. By taking the specifications of this wrist sensor, it has high stiffness. So high stiffness that provide accurate reading during a short time. Within a short time, being its high stiffness, we can measure its accurate reading. Second characteristic is compact design that ensures the device will not restrict the movement of the robot in workspace. And third one is linearity, having good linearity response between response of the force sensing element and applied force. And fourth one, low hysteresis and internal friction. Internal friction reduces the sensitivity of the force sensing element, and force have to overcome this friction. Usually the force has to overcome the friction generated, but in this case we have only a low friction, so thereby it is easier to overcome that friction. And also we have low distances that do not restore the position measuring device back to their original readings. Usually by applying a force to the strain gauges, it will move a little or displace a little. So by measuring that change, we can detect the applied force. Okay, so that's all with the force and torque sensor.